Okay, so the device you're watching this on, your phone, your computer, it's all powered by microchips. And we think of these chips as being made from silicon, that is, absolutely perfect. But what if I told you that their perfection actually depends on a secret ingredient, a tiny, deliberate imperfection? Today, we're going to pull back the curtain and find the most surprising hero hiding inside every single chip. Right, so when you imagine a silicon wafer, you probably picture this flawless, mirror-like disk. And for the folks in the multi-billion-dollar semiconductor industry, purity is basically their religion. Because even one single unwanted atom in the wrong place, it can be catastrophic. And these are the villains of our story. We're talking about microscopic little bits of metal, tiny impurities that can get in there and just wreck everything. They can short-circuit a device before it's even finished, ruining an entire multi-million-dollar batch of wafers. So how on earth do you protect against these invisible assassins? Well, the answer is not what you'd expect. At all. You'd think you'd need to make the silicon even more pure, right? But the solution is actually to fight one impurity with another, one that's added on purpose. Yeah, so what is this secret weapon? It's an element that we usually associate with, rust, corrosion, not exactly the stuff of high technology.
That's right, oxygen. It turns out this initially uninvited guest, as the research calls it, was actually a powerful ally in disguise. Engineers found that by intentionally dissolving a tiny, tiny amount of oxygen into the silicon, we're talking like 10 to 20 parts per million, basically nothing, they could create a chip that was way more robust and reliable.
So what does it actually do? What are its superpowers? Well, it makes the silicon wafer physically stronger, which is great, but its main job is this incredible thing called gettering. You can think of it like the oxygen atoms form these microscopic little cages, and these cages are perfectly designed to trap those nasty metallic impurities, pulling them away from the important areas of the chip where the transistors are. This one trick dramatically improves the yield, meaning more working chips per wafer, and it's a huge reason why the modern method of making silicon is so successful. But how? How does this actually happen at a microscopic level? I mean, how do the oxygen atoms know what to do? It all comes down to controlling this incredibly delicate balancing act, a process of creation, atom by atom. The key concept here is something called nucleation. And the best way to think about it is like raindrops forming in a cloud. You have all these individual water vapor molecules that are totally invisible, but when enough of them bump into each other and stick together, they hit a certain point, and poof, you have a raindrop. It's the exact same idea in silicon, but with oxygen atoms. So right after a silicon crystal is first grown, it's just swimming with these tiny, really unstable oxygen clusters. What this chart is showing you is that there's a ton of them, but they're all super small. And at this stage, they're not really useful yet. In fact, they can just dissolve right back into the silicon. They're just potential, waiting for a trigger. And that trigger is temperature. It's everything. At these relatively low temperatures, around 450 to 550 Celsius, the very first tiniest clusters start to form. Now, funnily enough, manufacturers usually try to avoid this specific temperature range, but it proves a really crucial point. Heat is what gets this whole party started. So this is the make or break moment. For one of these clusters to become a useful impurity trap, it has to grow to what's called a critical radius. It's the point of no return. If it's smaller than this size, it's unstable, it'll probably just fall apart. But if it can just grab one more atom and become just a little bit bigger than that critical size, it's locked in, it's committed, it's going to grow. So how do you get them over that hump? You bake them by cranking up the heat and annealing the silicon wafer at really high temperatures, like 1,000 degrees Celsius. You give those oxygen atoms the energy they need to zip around, find each other, and grow into big, stable clusters. And those clusters, those are the impurity traps that make our chips work. Okay, so that's the theory, and it's pretty amazing, but it brings up a really, really big question. How in the world do scientists actually see this happening? We're talking about things on an atomic scale. I mean, seriously, you can't just pull out a standard microscope for this. You're trying to count clusters of atoms inside a solid crystal. The challenge seems almost impossible, but the tools they've developed are just unbelievably cool. So, the main instrument they use is called a transmission electron microscope, or a TEM. It shoots a beam of electrons right through a super thin slice of the material, which lets them see the actual atomic structure. But even with a tool this powerful, there's a huge problem. How do you know exactly how thick your little slice of silicon is? If you don't know the thickness, you can't get an accurate count of the clusters. And this is where the scientists got seriously clever. They realized they didn't need to measure the sample directly. They could use another, different kind of defect that was already inside the silicon. As the research puts it, these other defects can, quote, provide a direct geometric measure of the thickness. And the trick they came up with is it's brilliant. Okay, so what they do is they find this specific kind of defect called a stacking fault. It's basically a flat plane that slices through the crystal at a perfect known angle. By using the microscope to measure the length of its shadow as it passes from the top of the sample to the bottom, they can use super simple geometry, like high school trig, to calculate the exact thickness of the sample at that precise spot. It's literally like using a crack at a window to figure out exactly how thick the glass is. Just genius.
So, being able to see those final, fully grown precipitates is one thing, but the real holy grail of this whole field is to see them before they grow, to actually find the invisible seeds that these crucial traps grow from.
And this slide really breaks down the challenge. On one side, you've got the grown precipitates. They're the workhorses, they're large, and they actually stretch and strain the silicon around them, which thankfully makes them pretty easy to see in the microscope. But the real prize, what everyone is hunting for, are these so-called latent clusters. They're the exact opposite. Tiny, unstrained, and basically invisible. And that's the core of the problem. These latent clusters, the all-important seeds, are so small and fit so perfectly into the silicon crystal that they don't create any strain. There's no contrast for the electron microscope to pick up. They're like perfect little ghosts, hiding in plain sight. Figuring out a way to find and study these invisible seeds, well, that's the next great frontier in making our technology even closer to perfect. It really makes you think, doesn't it? Inside the sleek, simple gadgets we use every single day, there's this hidden world of controlled chaos, of unlikely heroes and invisible battles being fought at the atomic level. It just makes you wonder, what other incredible, invisible secrets are engineered into the technology all around us, just waiting for us to find them?